Hey gang, let's refresh ourselves with sequences and series. So a sequence, it's an ordered progression of values. Usually it's going to be an ordered progression of numbers. It doesn't need to be numbers. You could have the sequence of alphabetical letters. That's a sequence. It follows a pattern. You can do a sequence of words, but we're primarily going to be doing a sequence of numbers. Now, for our sequence of numbers, the position in the sequence is a positive integer. It is a counting number. It starts at 1, continues to 2, 3, 4, 5, and our general term for the position in the sequence is n. That's going to be our general term. Now, for specific terms, in our actual sequence, so this is just the position in the sequence, we either call it a sub something or t sub something. The subscript is the position in the sequence. I'm not going to write the t's over and over again. So the subscript tells you where in the sequence you are, so a sub n means the nth term of the sequence, t sub n means the nth term of the sequence. The difference between using a and t is nothing. It doesn't matter. Just don't, if you've already been using a in a problem, don't switch over to using t. If you've already been using t, don't switch over to using a. It's just a variable. I don't know why it switches, but a lot of different textbook series use different letters for the same thing. But it doesn't matter. That's not important to us. So in a sequence, the terms in the sequence can be defined based on the pattern that the sequence follows. There are two ways to define a sequence. The first way is the explicit definition. So explicitly defining a sequence is writing an equation for the nth term in terms of its position in the sequence. So if we had something like 3n squared minus 2, if we wanted the fifth term, a sub 5 would equal 3 times 5 squared minus 2, so that's 73. So that means the fifth term would be 73. This is what the explicit definition does. It allows us to find a specific term based on its position in the sequence. Now, you do not need to state that n is an integer and n is greater than or equal to 1. These are implied. If you are working with sequences, and it is established that you are working with sequences, whether it's in like original directions, if it's in the header on the document, whatever, if it's established that you're working in sequences, you do not need to state this every single time. The only times you would need to state that is if nothing has led up to saying that's a sequence, or if you are changing your definition of n. If, say, you want n to start at 0, then you would need to state that. It is implied that n starts at 1, and it's an integer. So that's explicit definitions. So you don't need to state that unless there's nothing that would lead you to that assumption. So that's explicit. And the other way to define a sequence is recursively. When you define a sequence recursively, you are not just plugging into an equation. What you are doing is you are defining the sequence using previous terms. So if you want to find the nth term, you're doing something with the previous term. So let's say just like a sub n minus 1 plus 4. So if you were looking for the 7th term, you would need to know the 6th term in order to find out the 7th. You would add 4 to the 6th term, that would give you the 7th. But if you're going to do that, you need a jumping off point. So you need to know what your first term is. So let's say our first term was 5. So this tells us that this is the sequence starting at 5, and where you take a term, you add 4, and that gives you the next term. This is our recursive definition. So the sequence would actually follow 5, 9, 13, 17, 21, so on and so forth, following along that pattern. So that's a recursive definition of a sequence. All right. And that's it for the basics of sequences. We'll talk about arithmetic and geometric, and then eventually other sequences as well.